All right. Hi there, Chemistry 3101. This is the last chapter that we cover this summer, and this is the synthesis chapter. So, synthesis chapter is nothing more than a review of four of the chapters that you've studied already, chapter 7, 8, 9, and 10. Does that mean that you don't have to know chapters 1 through 6? Well, of course not, because, the concepts of stereochemistry and maybe acid-base chemistry, those kind of things are going to come up. But the focus, I would say the focus of this chapter is going to be chapters 7, 8, 9, and 10. So just to recap, chapter 7 was the chapter where we covered SN1, SN2, E1, and E2. Chapter 8 is the alkenes chapter. Chapter 9 was the alkynes chapter. And chapter 10 is the radicals chapter. So let's get into it here. And really, all we're focusing on in this chapter is nothing more than synthesis. What is synthesis? It's making a molecule. And if you think about any, prescription drug that you might have taken in your life or you've heard of, some chemists had to design a synthesis or a method of making that molecule, which will involve oftentimes many, many steps, And what we try to do, though, as a chemist, we try to minimize the number of steps and maximize the yields along the way. But what we're doing in this class so far is we're just learning some reactions like the one that you see here. If you have an alkene, right? This goes back to chapter 8. So you have an alkene. This compound actually has a common name. This is called isobutylene. It's actually used to make some kinds of rubber for basketballs and things like that. So isobutylene, and then if you want to do a halogenation of that, right? You want to add two bromines, and of course they're added in an anti-fashion. Here it's not important because you don't end up with any stereocenters, but in order to do that reaction, hopefully you remember that you would just need bromine, Br2, right? But bromine is a molecule in its pure form. You could include a solvent. I don't ask my students to do that. The textbook doesn't ask you to do that. But if you're wondering, what kind of solvent could you do this reaction in? A very common one would be dichloromethane. I mean, we're trying to get away from chlorinated solvents, but it is a very good choice. Now, what is the main point of this slide here, right? I'm sure that all of you remember bromination at this point right here, and you're going to see this come up a few times during this chapter. It says you have to master all the reactions and the reagents required before tackling multi-step synthesis problems. And so, how are you going to master all the reactions? Well, I'd say that, you could say that everybody has their own way of doing it in a way, but there's only so many ways that you can. Now, for me, I can tell you that personally, I just like to do practice problem after practice problem after practice problem. And then eventually they all kind of the reactions start to crystallize in my mind. Some people are really into flashcards. They keep flashing these cards over and over and over. Maybe that works for you. I've even had students who will just write the reaction over and over as if they were writing lines like a punishment or something. And that works for them. And so you've got to find what works best for you. And if you're sitting there and going, well, that just means I have to memorize. There's a lot of memorization, of course. Okay. I'd be a liar if I said there wasn't any memorization involved. There definitely is. Now, is there a way that we can simplify the memorization? In my mind, yes, there is. And that is to understand mechanisms, right? Now, mechanisms might not seem as big a deal when you're taking a course like this that is a remote synchronous class. However, the more that you understand mechanisms, the easier the organic chemistry becomes. So let's start out with this question, 11.1. You can see there's a lot of reactions on here, and we have to know them all. Identify reagents that can be used to accomplish each of the transformations shown below. If you're having trouble, the reagents for these transformations appear in the review of the reactions at the end of chapter 8. And so this is all alkene chemistry. Alkene chemistry, chapter 8. And I can't stress this enough. What it says at the end is you should try to identify the reagents yourself without help. Do not peek, okay? At least give it the old college try. So we're going to start with this question right here. So this reaction, the one I have in the blue circle. Could anybody answer me? Is this a Markovnikov or anti-Markovnikov addition of HBr across that double bond? Would this be Markovnikov or anti-Markovnikov? Exactly. Thank you. This is a Markovnikov addition. And so for that, we're going to need HBr, right? No peroxides required. I'm going to put a star by this one because you should know the mechanism of that reaction. Now, if we go counterclockwise, What about this reaction here? This is an anti-Markovnikov addition of HBr, right? The carbon that is richer in hydrogens, in this case, this hydrogen happens to take the bromine. So again, it's the opposite of Markovnikov addition. So I'm going to need HBr, but I also need an organic peroxide, okay? And I would say you should also be, at least partially familiar with that mechanism, which is covered in chapter 10, right? Remember that once you have the halogen addition, once the bromine radical adds, you form the most stable radical, right? Which would be this intermediate here. Then you do a hydrogen abstraction. So you should be somewhat familiar with that reaction. Let me ask you another question. What about this reaction here, where I'm taking methyl cyclohexane and I'm converting it into 1-bromo, 1-methyl cyclohexane? Could anybody give me the conditions for that? One of them is a reagent we've already seen in the slides today. I'm going to need, so it's not going to be HBr in this case, right? So here we're just starting with a plain old alkane. Okay, this is an alkane, and then we want to add a bromine to it. So this is a chapter 10 reaction, right? This is a radical reaction. This is the reaction where we use bromine and light or heat, right? This is a free radical reaction. Remember this reaction well, my friends. The only option you have when you're starting out with an alkane, now this is a cycloalkane, but I'll just put alkane here in quotations. The only possibility you have is to do a halogenation. That is it. There is nothing else you can do but a halogenation when you're given an alkene. Okay, so now let's say we want to take this alkyl bromide and we want to convert it to the alkene. Would I want to use a hindered base in this case or an unhindered base? Could anybody help me out with that one? If I want to pull off this proton, right? I want to pull off this proton here. I'm going to have to use an unhindered base to do that. Exactly. Thanks, Sarah. Yeah, so I'd use something like sodium ethoxide or sodium methoxide, for example. So let's scribble that in here. We'll put sodium ethoxide. It seems to be one that the book likes a lot. Now, the question here doesn't mention the Hoffman alkene, but we could practice that one here. If we wanted to make this compound, is called methylene cyclohexane. If we wanted to make that, we would use a hindered base like potassium T-butoxide or DBU or DBN, some kind of non-nucleophilic base. All right, let's keep going let's go in a counterclockwise fashion, I guess. What if I wanted to do this reaction here? Is this a Markovnikov or anti-Markovnikov addition of water? Yes, again, this is a Markovnikov addition. So for that, we just need some aqueous acid. Again, I would say this is a mechanism that is extremely important. So an extremely important mechanism. So let me just fix this. Want to know that mechanism for sure. The next one is anti-Markovnikov addition of water across a double bond. Remember that is achieved by a syn addition. So we're going to put here borane and THF in the first step. And then in the second step, we use hydrogen peroxide and sodium hydroxide. The next one, we're taking the alkene and we're converting it to an alkane. So for that, that's a hydrogenation reaction. So we need hydrogen and palladium, platinum, or nickel. I'll just pick palladium arbitrarily. The next one is the halogenation, right, which is achieved via an anti-addition. So for that, we need Br2, and that's the reaction that we looked at on the previous slide. The next one is the formation of a halohydrin. So I just want to remind you, this is called a halohydrin. And I've told you this once this summer, that you don't really use halohydrins until you get to chapter 12. I teach you how to use a halohydrin to make an epoxide or an oxirane, but that's another kettle of fish. But the only difference between this reaction and the bromination is that you use bromine, but you do the reaction in water as your solvent. So you form the bromonium ion, and then water comes in as a nucleophile and opens that ring. Then you do a proton transfer to make the halohydrin. All right, what about the next one? If we want to do an anti-dihydroxylation, could anybody give me one of the steps for this reaction, an anti-dihydroxylation? There's two steps involved here. What would the first step be? Exactly, thank you. Thanks, Sarah. It's MCPBA or some kind of peroxy acid. So I was going to write MCPBA. Sarah says, let's write this RCO3H, right? A peroxy acid. Okay, and then in the second step, we're going to crack that epoxide open with aqueous acid. Good. The next one is a reaction that we really did learn a whole holy host of ways of making a cis-diol, so syn addition. But I would say the best one would be to use a catalytic amount of osmium tetroxide. So we'll put osmium tetroxide catalytic amount, and then you use NMO as your co-oxidant. And NMO is N-methylmorpholine N oxide. And the last one, could anybody give me the reagents for the last one? You're breaking this ring open. We call this an ozonolysis reaction or oxidative cleavage. Either one. Yes, there we go. Man, my students are fast. All right. So the answer is number 1 is going to be ozone, and number 2 is dimethyl sulfide. Or the second step could be zinc and water. It only comes up once in the textbook. I don't even remember my students really using it a whole lot. I'd say the only reaction really that's covered in chapter 8 that isn't on here is Markovnikov addition when you want to avoid a carbocation rearrangement. So that is oxymercuration, demercuration. And so, yeah, I don't think it's even shown on here whatsoever. And so you should know the conditions for oxymercuration, demercuration. So that's mercuric acetate in water in the first step. And then the second step is sodium borohydride. So that's a Markovnikov addition of water, but we're avoiding a carbocation rearrangement. All right, I think that's the only one that's not shown in here. All right, let's move on to question number 2. The questions are very long at the beginning. It says, identify the reagents that can be used to accomplish each of these transformations. If you're having trouble, this is found in chapter 9. So this is the alkynes chapter. All right, so, and again, please try to do these kinds of questions without looking at the textbook. So I'm going to help you through the first couple of them here because there's some nuances. But this very first one, we'll start with the one that's pointing straight up. This is obviously a Markovnikov addition of HBr. And so you're going to need HBr. But since it's only adding once, I would just write one equivalent of HBr. Okay, if you just put HBr, that's fine. But I would just write specifically that it's one equivalent. And then if I wanted to add a second molecule of HBr, so you can see that we do another Markovnikov addition of HBr here. I mean, you could just do excess HBr if you wanted to, or you could just write HBr is fine. Either one would be totally acceptable in this case. All right, let's take a look at these two reactions. So this reaction here, where we take a geminal dibromide and we convert it to an alkyne, and the one where we take a vicinal dibromide and convert it into an alkyne. And remember that both of these reactions are identical. It's the same conditions for both. So we're going to put here step 1 is excess sodium amide, and step 2 is water. Quench it with water. Same thing for the next one. First step is excess sodium amide, and step 2 is water. And what's interesting about this reaction is it is the only way that we know how to make an alkyne without a change in a carbon skeleton, right? We can make an alkyne by, changing a carbon skeleton, but we have no way to do it without it. All right, let's take a look at the one that's going straight down. So this one here, so this is another ozonolysis reaction. The first step is going to be ozone. Does anybody remember what the reagent in the second step is? First step is ozone. Second step would be, thank you, is water. Good. All right. The next one, you're just halogenating the heck out of it, this reaction here. So for this one, we would just use excess bromine. I mean, there's not much else you could do with that. This one here. Now, the next one, you're only adding one molecule of bromine. So I would just put one equivalent of bromine. So I'd put one equivalent of bromine like that. All right, keep going in counterclockwise fashion. The next reaction is one of the most important reactions, arguably, of the entire course, because in this reaction, you learn how to make a carbon-carbon bond. Right, so the first step is going to be sodium amide to do the deprotonation. We're only adding a methyl group here. So our electrophile would be methyl iodide in this case. Let's keep going. We'll worry about all these reductions after. If we keep moving, what about this one here? Is this a Markovnikov, or have the little red circle? Is that Markovnikov or anti-Markovnikov addition of water across a triple bond? We make an enol, good, which tautomerizes to give us an aldehyde. So the first step is going to be 9-BBN or some kind of hindered borane. And then the second step is hydrogen peroxide and sodium hydroxide. And then the last one is a Markovnikov addition of water, which cannot be affected with just sulfuric acid and water. You have to have sulfuric acid and mercuric sulfate in water. Okay, and then the last three, we have the reduction to a cisalkene, the reduction to a transalkene, and then we also have just the complete and total annihilation of the triple bond. So for this one, it's just hydrogen and a catalyst like palladium. If we want to make the cisalkene, that uses Lindlar's catalyst. So hydrogen and Lindlar's catalyst. If you put poison catalyst, that's totally fine. And then to do the trans, we're going to use sodium metal reduction. So we use sodium in liquid ammonia. And there you have it. So those are all the alkyne reactions. I can't think of anything that's being missed on here. Now, the rest of the slides like this are just kind of a yammering on of all the different reactions that we've learned, but I'm going to try to frame it in terms of things that you might be asked to do, okay? So two-step synthesis, okay? What's a two-step synthesis? Well, a common one that we run into is moving a functional group around. So let's say you wanted to move a bromine. Let's say you wanted to move a bromine, you know, to convert it from a secondary alkyl halide to a tertiary alkyl halide. Well, that's going to involve an elimination followed by an addition. So for the first step, for the elimination, if this is your alpha carbon, you have a beta proton here, and then you also have a beta proton here. Well, we want to pull off the beta proton in blue, and so we're going to use an unhindered base like sodium methoxide. And then for the next part, we need to do a Markovnikov addition of HBr. And so for that, we're just going to use HBr. So just a two-step synthesis, but again, it borrows two reactions that were covered in a question 11.1, right? All right, so we've covered making a Zaitsev alkene and then doing a Markovnikov addition. So you see that it's shown here. Now you could also use a hindered base like potassium T-butoxide in order to give you the Hoffman alkene. So this is the Hoffman alkene here. And then you could do an anti-Markovnikov addition. And so you can see you've got a lot of power in terms of moving a bromine atom around a molecule. Now, what if it's a hydroxyl? Well, then it gets a little bit more interesting because we know that hydroxyl, an OH group, an alcohol, this is not a good leaving group. But we did learn a way to convert it into a good leaving group using tosyl chloride and pyridine. It's the first time we've seen that today. And when you do that, what that would do is that would convert the hydroxyl to what we call a tosylate. And now you convert a poor leaving group into a good leaving group. And so you can do an elimination like a Zaitsev elimination to make this product and then a Markovnikov addition. All right. We could also use that good leaving group to do an elimination where we make the Hoffman alkene, and then we can do an anti-Markovnikov addition. And of course, I do want to highlight this reaction right here, which is one that was not shown on the previous slides. But this is how we do the Markovnikov addition of water and avoid carbocation rearrangements. Because if you were to use this alkene to do a Markovnikov addition of water just using H3O+, you would end up with this intermediate. I'll just kind of scribble it in here. Right, you'd end up with this carbocation, but that is going to do a hydride shift, right? So you've always got to be on the lookout for those kinds of things. A good organic chemist, she or he should always be on the lookout for any kind of carbocation rearrangement that can occur. So we've talked about moving a halogen around. Now, what about moving a pi bond around? Well, in order to do that, you've got to know your hindered bases from your unhindered bases and when to use them. Right, we know that we could do a Markovnikov addition of HBr across this alkene to make this tertiary alkyl bromide. But if this is our alpha carbon, then we have this beta carbon in blue, and then we have this beta carbon in black. If we want to pull off the beta carbon in black, we would have to use a hindered base like potassium T-butoxide. You could also use DBU, DBN, that would be fine with me and anybody else, okay? But, and this is meant to be, you know, it's not meant to sound mean or anything. These are the words of David Klein, but it says the reagents we choose, or where is it? Yeah, the reagents we choose depend on the regioselectivity we need. And so you've got to know the difference between Markovnikov and anti-Markovnikov addition. You have to know this very, very well. And what I was trying to get to was this statement right here, which might look like it's mean or something. It looks like a meanie wrote this, okay? But believe me, Mr. Dion is no meanie. And it says here, look, we have no chance, okay? No chance. It doesn't sound very nice. But anyhow, it says you have no chance to get this far unless we can easily recall all the possible reagents and reaction conditions first. I mean, it's a politically correct way of saying you've got to know your reactants inside out in order to master the content here. Now, I'm not going to go over every reaction in here, but again, you can see it's a plethora of Markovnikov and anti-Markovnikov and Zaitsev and Hoffman eliminations. And so you've got to really know that stuff frontwards and backwards in order to affect all these synthetic transformations here. So we talked about radical bromination, and I can't stress this enough. If you're ever given an alkane or a cycloalkane as a starting material, the only thing that you've got, the only arrow you have in your quiver is literally bromine and light. That is it, or bromine and heat. There's nothing else that we could do. I guess you could burn it, but that doesn't really help you a whole lot, combustion. And then we've already covered elimination. And so if you remember, at the end of chapter 9, we actually had this scheme in the chapter, and it said you've learned everything except this transformation here, how to go from an alkane and then convert it to an alkene. And now we know how to do it by a bromination and then an elimination. So we know all of these different reactions here. So with all that in mind, let's see if we can come up with some syntheses for these 4 problems here. And it's just trying to make sense of all the reactions that we've covered. Now, if we have no change to the carbon skeleton in the first problem, we're starting it with 1, 2, 3, 4, 5, 6 carbons, and then the final product has 6 carbons. So if there's no change in the carbon skeleton, the only possible way you know how to make this alkyne would be from the vicinal dibromide, right? So now the question becomes, well, how do I get from here to here? And I think you all know the answer to that, right? The answer is going to be to brominate that. So without drawing out every single intermediate, we're going to put bromine as the first step, and that would make the compound in red. Now we can do the double elimination followed by the proton transfer to make the alkyne. So now we're going to treat it with excess sodium amide. All right. And then in the third step, we're going to treat it with water, and that's going to do the protonation, and I'm done. That's all there is to it. Now, I don't mean to make light of the question or anything, but that's it. It's a 3-step synthesis. Give me a thumbs up if you're with me on that synthesis. And again, when I say that, it doesn't just mean make me feel good. If you have a question, do not hesitate to stop me at any point. Mr. Dion is always happy to talk about any kind of problem that you have here. So let's take a look at this question B, okay? So if we examine this compound, I think you could all identify this as a primary alkyl bromide, okay? If this, I'm just going to ask you without writing anything. In the first compound here, how many types of beta protons are there? How many types of beta protons are in this molecule? Let's see if we can use some of the vernacular, right? The correct vernacular here. How many types of beta protons are there in this molecule? There's only one, right, Sean? This is my alpha carbon, so there's literally one beta proton. That is it. Nothing else. There's just one beta proton. So we know that the first step is going to have to be an elimination, because if we do a little retrosynthetic treatment here, we know that the only way for us to make this tertiary alkyl bromide, or the best way, would be to start with this alkene. Now, can we do an elimination to remove that proton to make the alkene? Yes, and there's many bases that we could use for the first step. You could use T-butoxide, you could use DBU, DBN, And the reason you'd want to use a hindered base here, even though there's only one type of proton, is because you want to suppress any SN2, right? Because this is a primary alkyl halide. You do not want SN2. So I'm going to put here T-butoxide. And I'm going to make a little note here. I'm going to put suppresses SN2. All right, so that's our first step. That makes the compound in blue. And then once we have the compound in blue, we just have to do a Markovnikov addition of HBr, my friends, and we are done. Done like dinner. All right, let's take a look at C. I'm going to go over here just so I have a little bit more room. And so we're looking at C. So we start with this. This is methylene cyclopentane. And then we want to make 1-methyl cyclopentene, this molecule here. So what do you think the first thing I would want to do here would be? Would it be a Markovnikov or an anti-Markovnikov addition of HBr, do you think? What do you think? What's a hunch? It's going to be Markovnikov, isn't it, right? Anti-Markovnikov isn't going to get us anywhere. So if we do a Markovnikov addition of HBr, right, the rich are going to get richer. So we're going to end up with this carbocation. And then in the next step, our bromide is going to come in as a nucleophile in here, like this. And so we end up with this compound, 1-bromo, 1-methyl cyclohexane. And now if we want to make this compound, we're going to have to remove this beta proton. So for that, we're going to use an unhindered base like sodium ethoxide. So if we write the ethoxide ion like this, that gives us a chance to draw the mechanism where we form the double bond and lose the bromine. And so this is a total of 2 steps. Step 1 is HBr, and step 2 is sodium ethoxide. Now, there's nothing wrong with this synthesis. It's fine. It's 2 steps. Did anybody come up with another idea for this one? Does anybody have a second idea? What if I did a Markovnikov addition of water across this and made an alcohol? So if I treated this molecule, so again, we're trying to get to this compound. If I treated this with H3O plus, right, in the first step, so step 1, H3O plus, that is going to do a Markovnikov addition, right? So I end up with this carbocation. Water's going to come in as a nucleophile. I get a proton, so I'll go nucleophilic attack, proton transfer, and I'm going to end up with this alcohol. Now, is there a way to go from this alcohol to this alkene? You guys remember my favorite reaction in the chapter, or in the whole beginning of Organic 1? If I take an alcohol and I want to make the most substituted alkene, exactly, all I have to do is cook it up in sulfuric acid, and you're done. Sulfuric acid and heat. Now, I would say there's one reaction is not better than the other. So for the first step, you put H3O plus dilute. Second step, you could put H3O plus concentrated. It sounds weird, but yes, that would work, okay? And if you want to put heat in here, that's totally fine. Yep, because it would drive water off of the reaction. Anyhow, I thought I'd kind of share that with you as I thought it was interesting. All right, and the last one. So I'm going to go back here to D. So we're going to solve D now. What about D? I'm starting it with methyl cyclopentane. What's the only possibility I have for the first step? The only possibility for the first step. There's only one possible. Exactly. Thanks, Kiana. So I'm going to take that molecule and I'm going to treat it with bromine and light. And that's going to make the tertiary alkyl bromide like this. Now I need to pull off this beta proton. So for that, I would use an unhindered base like sodium ethoxide. And that's going to give me the Zaitsev alkene. And I am done. There you go. Not too bad. Now you notice that what these problems all have in common is that there's no change in the carbon skeleton. So all of these problems, so no change in carbon skeleton, okay? It doesn't change whatsoever. Now what happens if we want to change the carbon skeleton? Now, not to get ahead of the game, but when you get into organic chemistry too, so chemistry 3111 at UCCS, you learn a lot of ways to change a carbon skeleton, to make it bigger, to make it smaller. But in this class, we only learned a few ways to do it. So let's take a look here. It says for some transformations, it might be necessary to add or remove carbons. So when a synthesis requires a carbon skeleton to be altered, you have to be able to recall all those reactions. So maybe you need to make the skeleton bigger. You need to make an alkanide and then do an SN2 with that. Maybe you need to make it smaller. You would use oxidative cleavage, right? Ozone. There's very few things that we've learned that break up or add carbon. So it says here only one transformation has been learned to add carbons. Literally one thing. So you have to make an alkanide. If you make an alkanide, then you can do an SN2, right? Nucleophilic attack, loss of leaving group. And so the second, the electrophile has to be either a methyl alkyl halide or a primary alkyl halide, you know, something like this. So it has to be either methyl or primary. It can't be secondary or tertiary because in that case, elimination will predominate. But there you go. That's the only thing that we've got. Now, again, in organic too, you learn a whole bunch of ways of doing this. But for now, it's all we've got. And then when it comes to breaking a carbon skeleton down, we've only got a few options here. And one of them is to use ozonolysis, which we know will cleave a carbon-carbon double bond, and it can also cleave a carbon-carbon triple bond. So this is the ozonolysis of an alkene. We already looked at ozonolysis of an alkyne today, which requires ozone followed by treatment with water. So with all that in mind, let's take a look at these problems here. Now the first one, we're taking this molecule here. Who could give me a name for this molecule that I have in the blue circle? I actually asked this on a quiz last semester. I said, what's the name of this molecule? Exactly, it's acetylene. Right, so this is acetylene. You could call it propine, but people might, you know, call the police or something, be like, this person is severely intoxicated. I'm kidding. But anyhow, so look, we have a methyl group on one side, and then we have an ethyl group on the other side. Is the order of addition important here? Do I have to add one over the other first? No, not at all. So let's take a look. What we're going to do is we're going to take this molecule and we're going to treat it with sodium amide, and that is going to make the alkanide. Then we're going to treat it with iodomethane. That will add the methyl group. Then we're going to do the same thing to add the ethyl group. We're going to treat this with sodium amide. That will convert it into an alkanide. And then we're going to treat it with ethyl iodide. And that is going to make a compound that we want. Done. A total of 4 steps. And for the last one, kind of an interesting problem because now they give you the electrophile instead of the nucleophile to work with. And so for this one, all you have to do is hit it with sodium acetylide, which is a reagent that you can assume that you have, right? This is just going to do your SN2, nucleophilic attack, loss of leaving group, like that. And if you're really hung up on it and you want to write out how to make that compound, be my guest. I guess you could say, well, I would make this compound from, you know, I would make this compound from acetylene and I would treat it with sodium amide, right? And that would give me sodium acetylide. If you have to write that down to feel better about yourself, that's totally fine. I don't have a problem with that. But there you go. So let's take a look at the next section, which is how to approach a synthesis problem. I would say before you do any of these, I would say, you know, the main thing you've got to do is master questions 11.1 and 11.2. You know, the questions that we looked at that had all the reactions from chapter 8 and chapter 9. I'd start there, you know, and they even had a question from chapter 10 squeezed in there too. And then I'd say, is there a change to carbon skeleton? Are you adding or removing? You know, are you moving a functional group around? And, you know, you really do have to work through many examples in organic chemistry. You know, this is one of the great equalizers in this subject in organic chemistry is that it's very rare that a person could say, I just get it, I just get it. Which, sometimes happens in a course like math, maybe. Somebody says, oh, I just kind of figured it out. But in organic chemistry, it usually takes a lot of heavy lifting for most people to master the content. So let's say you wanted to take this alkyne. So this is 1-pentyne, and then we want to convert it into this transalkene. Well, you can see that we're going from a total of 5 carbons to a total of 7 carbons. So we're going to have to treat this with sodium amide to rip off the proton. And then in the second step, we're going to treat it with ethyl iodide. Now, when you do that, you're going to end up with this intermediate, right? 1, 2, 3, right? And then you're going to have this guy here. So now if you want to reduce that to the transalkene, you're going to use sodium metal reduction. All right, so again, the book kind of goes or the slides kind of go all through the whole thing here, but I'm pretty sure that all of you could have figured that out pretty quickly. So with that in mind, let's try to do some other changes to carbon skeleton. Some of them are simpler than others. Let's take a look at the first one. So we're starting it with a compound that has a total of 5 carbons, and then we're ending up with something with 8 carbons. So we've got 5 carbons, and then we want 8 carbons. So let's see here. In the first step, we're going to take this alkyne, and we need to add these 3 carbons, right? So we're going to take it, and we're going to treat it with, the arrow's too long. We're going to treat it with sodium amide, and then we're going to treat it with propyl iodide. So 1, 2, 3 carbons, and then an iodine, like that. And that is going to give us this compound, 1, 2, 3, 1, 2, 3, like that. And now if we want to reduce it to the cis alkene, can anybody remind me about how to do that? To the cis alkene? Thanks. Yep. Thanks, Eric. So it's going to be hydrogen and Lindlar's. Yes. Lindlar's catalyst. Good. All right. Next one is well, I guess I should write down the answer. 2, 3. 1, 2, 3. There we go. All right. So the next question. So let me just make some room here. All right, next question. We're taking a compound that has 6 carbons, and then we're making something that's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. This one's kind of an interesting problem because, really the only way to add these 3 carbons is to use this alkanide. So if you had this alkanide, then you could just do an SN2 on a primary alkyl halide like this. Right, if you had this compound. So to make that compound from the starting material, you just need to do an anti-Markovnikov addition of HBr. So HBr and peroxides would give you this compound. All right, and then you could just do your SN2 with your acetylide. And you're like, well, this acetylide has 3 carbons. It's not just sodium acetylide. Yeah, but you can assume that you have small reagents like this. So again, that would just do the SN2. And that's going to give you the alkyne. So we have, let's see here. There we have 1, 2, and then we have 1, 2, 3. And there we go. So that's going to give us this compound. And then to reduce it to the transalkene, we're going to use sodium metal reduction. Give me a thumbs up if you're with me on that one. At least on the rationale for it. Not for I solved this in 10 seconds flat or something like that. All right, great. Okay, I don't know if I put enough room to solve the last one, so let's scribble it over here. So this is E. So we're going to take this alkene, and we want to convert it into a terminal alkyne. So this one is going to involve a lot of moving bromine around, right? Because we're starting out with something that has 5 carbons, and then we have 1, 2, 3, 4, 5, 6, 7 carbons. And so hopefully you can see that you would want to make this compound from this, right? If you could make this primary alkyl bromide, then you can just treat it with sodium acetylide and you're done, right? Just SN2 and it's over. So how do we go from here to here? Well, there's no way to do it directly, is there? The first thing you've got to do is either a Markovnikov or an anti-Markovnikov addition of HBr. Could anybody tell me which one would I want to do, a Markovnikov or an anti-Markovnikov to start, do you think? Remember, I want to get the bromine here eventually. What do you think the best? Yes, exactly. Thanks, John. It would be anti-Markovnikov, exactly. So that would give me something that looks like this, right? And now we're getting closer, right? Because if we treated it now with a hindered base, like potassium T-butoxide, that would give me this alkene, and you can clearly see how we can get from here to the compound written in blue. We need to do another anti-Markovnikov addition of HBr, and that is going to put the bromine out on the end so that we have a primary alkyl bromide. And then in the very end, we're going to treat this with sodium acetylide, and you are done. That's it. SN2 again, and that gives you the final product. So something that, is really handy for a chemist is doing this approach, right? Is going backwards. So if you're ever stuck on a synthesis problem, and this can happen a lot in organic too, where we have reactions that are synthesis that take maybe 10 steps or something, and students will get kind of overwhelmed. Well, if that happens, just think about, well, what's the last step going to be? How many ways do I know to make this carbon-carbon bond at the end, right? Because I've got to create a bond between these two carbons in red. Well, it's going to have to be an SN2 because I'm going to have to make it from acetylide, right? So then you start thinking, well, I've got to have this primary alkyl halide, and that, and then you say, well, how am I going to make that? Well, I could make this from this alkene, right? I could do an right, which is this compound, right? So you're just kind of going backwards stepwise. And believe it or not, somebody won a Nobel Prize for this, okay? Or actually, I should say the person who developed retrosynthesis won a Nobel Prize. Maybe I could put it that way. But retrosynthesis is a very powerful tool, not only for seasoned chemists, but for also for people learning the subject like you. So it's just putting the last step first, and then just kind of going backwards from there. And so it can really get you out of a jam. I said, give me a thumbs up. Is there anybody who uses retrosynthetic analysis already? Or sometimes if you get stuck, you just say, I'll just go backwards one step. Yeah, absolutely. It's really handy. So I encourage you to try this, So let's say you had this reaction here. You want to come up with all the reagents. Well, the first thing that we can see is there's how many ways do we have to make a primary alcohol, So let's say you make that primary alcohol and then you want to make this alkyne. Well, really, I mean, for the last step, that the only possibility that you're going to have is to have a vicinal dibromide, right? But then you're like, well, how would I make that? The only way I know how to make that is from the alkene. Oops, I'm missing a carbon here, right? So then it makes it a little simpler. And then you're like, well, how am I going to make that? I could make it from, if I had something that had a good leaving group, like this. Okay, so I'll put leaving group like this, and then you're thinking, well, how do I convert a hydroxyl to a leaving group, right? So you're just going backwards and backwards and backwards like that. So I've kind of covered the whole thing already, right? So you can see it goes through a lot of steps here, but basically this is the answer shown down here at the bottom. So you need to treat this with tosyl chloride to make the tosylate, then a hindered base that gives you this alkene, then you do a bromine addition, then a double elimination followed by a proton transfer, and there you have it. So that's it. Give me a thumbs up if you understand the synthesis that has the yellow line underneath it. If you're like, I at least understand it. I'm not saying that you would have come up with it in 10 seconds flat or anything. That's not about speed, okay? That's definitely not part of the course. All right, so with that in mind, I wanted to take a look at some problems that are maybe a little more complex, involve a few more steps. So I think this is a good point for us to stop. And even if you're watching the video at home, this would be a very good stopping point for you to just grab a pencil, piece of paper, and try these, okay? Like for example, and I'm not going to give away the first one, but you're starting out with something that's got 2 carbons, and then you're ending up with something that's got 4 carbons, okay? We only know one way to do that, to increase the number of carbons in the skeleton. And then also, I mentioned this morning. This is a halohydrin, right? We only know one way, to make a halohydrin. I'm not going to cover that right now. I want you to try it. And then if you look at the next one, there's no change in the carbon skeleton here, right? But if you're starting it with an alkane, there's only one possibility for the first reaction, right? That might, get you where you want to go with that one. And the same thing for the last one. There's only one possibility for the first step. So again, I'm going to pause here, stop, take a little break, and I would like you to at least give these the old college try, so to speak, and then we're going to come back and take a peek at them.